So yeah, I'm going to be moving to ETH Zurich. I'll be looking for PhD students and postdocs. If you're interested, get in touch. I'm going to talk about hypernetworks and quantum extensions of hypernetworks. And so I come from a slightly different background. I come from applying or thinking about using machine learning or classical machine learning to solve quantum problems. And this is my first, the first time I tried the other way around, like using quantum computers and so on. So we'll see, but I'm going to be making all those mistakes that Maria and Nathan said you shouldn't do, but I did anyways. So you'll see how that looks like. So I guess there's a lot of excitement in deep learning, an explosion of research and results in computer vision, natural language processing, machine translation, self-driving cars and physics, chemistry, finance, basically all science on using neural networks and deep learning to challenge or to tackle problems in these fields. And I'd say the progress is driven by the availability of data sets, specialized hardware, and outstanding algorithmic developments that have ushered a new generation of models displaying unprecedented accuracy and wide array of important problems in science. And there's a bunch of examples, but I have a couple. So diffusion models, which basically generate images. They're very impressive for image generation that suggests that art will change. And here I have an example. It's called DALL-E. It's a model where you prompt the model with natural language, and it draws artistic pictures, okay? So I used it. I said a sunset in Toronto wavefront in the synthwave style, and this is what you get. So it's very pretty and very artistic. So this is pretty much captures everything I said here. So these models are very powerful. They're going to change art and many more things. Then there's natural language processing, which is this branch of computer science or linguistics, machine learning, which is concerned with giving computers the ability to process text and spoken words in a similar way as humans do it. It's used in machine translation when you type something on Google Translate. So you're using machine translation based on neural networks, speech recognition, sentiment analysis, and more. So there's a lot of excitement about this in particular, NLP, natural language processing. And there are examples. So one of them is Galactic, a large language model for science, which was introduced last year, where you prompt a scientific topic and this language model writes a manuscript for you. So it's pretty interesting, but it created some problems. So Facebook or Meta had to shut it down because it was basically writing pseudoscientific papers, and people were using them to their advantage. So that's pretty dangerous. But these models are very powerful. So this is me, like we quoted, we used Galactic, and we asked it to write about recurrent neural network wave functions, which is one of our papers, and it produced something really reasonable, basically saying that you can write a wave function as in terms of recurrent neural network, which was what we had done at the time, or a few years before this paper came out, and so it's very impressive because it's nearly correct, and so it's very impressive. The other example that people know about already is ChatGPT, which is a machine learning model which interacts in a conversational way. It has a dialogue format that makes it possible for ChatGPT to answer follow-up questions and admit mistakes and challenge incorrect premises, and it's all over the news. So you can see that, or it was at this point. I mean, now it's a different world now. People believe these models will have deep technological and educational implications. ChatGPT can pass the United States medical license exam and bar exam as well for law. So it's crazy. It's going to change the world, and it's changing as we speak. But sometimes it fails. So I did ask ChatGPT to draw Mona Lisa, okay, using ASCII art, and this is the attempt. So it can fail too, or somewhat fail, although now we know Mona Lisa is smiling, as opposed to not knowing what it's doing.
By the way, it's amazing at getting that drawing to circuit diagrams.
Is it?
It is.
Okay. maybe there's more data. But anyway, so that's a quote-unquote failure mode. But I guess more seriously, so training these models is very expensive. So these advances depend on the availability of specialized computational resources such as graphics and tensor processing units, which demand a high electric consumption. In particular, a key or an important computational part that is very expensive is in the machine learning pipeline is the hyperparameter optimization and the architectural search. So you have to look over the space of models and hyperparameters, and you do that for, and then for each of these choices, you typically do a training run for the model that you have defined. And so this is such that training GPT-3, which was the earlier version of ChatGPT, cost about 27 million in electricity plus infrastructure. So GPT-4, I don't think it's known, but it should be along the lines of millions. Yes?
More than 200 million.
Okay, more than 200 million. So it's very expensive and also not very kind to the environment because of the electric bill. So there's a possible solution, which is quantization of weights and biases. So this is nothing to do with quantum mechanics. This is just taking the weights and biases and making them low precision. And the extreme limit is when you make the weights and biases binary, so up and down or 1 or 0. And so these binary neural networks are just basically neural networks with binary weights and biases and activations, and this partially alleviate these issues as they're computationally friendly or efficient, and they're more energy efficient, okay? There's right away a 32-fold reduction in memory if you're using float 32 to start with. They're robust to adversarial attacks, and you can use specialized hardware implementations that increase the computational speed and improve the energy efficiency. However, so the parameter, hyperparameter, and architectural choices remain computationally expensive because you still have to train these binarized neural networks. So traditionally, so when you're training a neural network or a binary neural network, there are two nested loops. There's an outer optimization where you loop through the hyperparameters and architectural choices in your neural network on a validation set, okay? And then for each of a possible choice of hyperparameters and architectural choices, there's an inner optimization which adjusts the weight of the neural network on a training set, okay? And this nested optimization it remains the most computationally demanding task in machine learning, in classical machine learning. Even some people say that entails an unsustainable carbon footprint given the sizes of these models. And so the call was that we should try to find computationally efficient hardware and algorithms to train and search for these architectures and models. And so typically what you do is you have this inner and outer optimization, and you have some sort of objective function, okay? And a training data consisting of, I don't know, NT data points. You have a loss function that depends on the style of training you're trying to achieve. For instance, mean square error or negative log likelihood if you're doing unsupervised learning. And you have some sort of neural network whose input is xi, has some weights, biases, architectural choices, and then some label possibly if you're doing supervised learning, and then some loss function that you use. So this objective becomes then a real Boolean function of the binary hyperparameters or the parameters of the neural network. And this is what the machine learning community or the machine learning workflow aims at optimizing this real Boolean function of the, if we're talking about binary neural nets, then that should be optimized. Okay. Yeah.
So just a question: if you're optimizing a bunch of binary weights here, what types of methods are used for it, like simulation annealing, or?
Yes, the different techniques. So there are techniques such as simulated annealing, but then there's other ones that relax the problem to a continuous version. And so they use back propagation, the usual techniques, and then at the end they come back and binarize the weights again. And so there's different techniques. So techniques where you do not go through a relaxation of the problem, so simulated annealing or parallel tempering, and then there's ones where you relax the problem into a continuous problem, and at the end you binarize the solution. Yep.
Could you not, instead of relaxing it and going to a continuous problem, how can I say this? You use the theory, you pretend as if you have a continuous problem, but apply this to your binary problem approximation. Do you know what I mean? So for example, you go, with binary it's hard to think about, but if you think of tensor processing units where you actually have only 8 bits or whatever it is, but you pretend you've got actually a continuous number there. So you use the routines of continuous optimization, but you just hope it doesn't disturb by your final precision.
So that's more or less what one of these algorithms work. Like you think about the forward propagation as a binary problem, but then when you do back propagation, you think about these variables as continuous, and then as you make changes using following the gradient descent, then you say, okay, I'm going to go with up or down or 0 and 1. Mm-hmm. It's an approximation, of course, but this is how the machine learning community do it. Okay, this is how they do it. All right. So one other connection with what I'm going to be talking about is the idea of a hypernetwork. Okay, and so hypernetworks are a family of approaches where you use one network, also known as the hypernetwork, to generate the weights of another network. Okay, and so here you are throwing, I don't know, some classification task on a neural network that I don't know, classifies your images into some sort of category, and then you have a hypernetwork that produces the weights and biases of the of your neural network. Okay, and they're used all over the place too. They're used in natural language processing, computer vision. They're used for hyperparameter tuning and architectural search and so on.
So would the image be fed into the hypernetwork as well, or?
There are examples where you input the data set actually into the hypernetwork, and then that helps you, but you can also not do that, right? Like you can also just fed the image to the neural net that will be eventually used for inference at the end. Yep.
Is this related to like learning-to-learn optimizers, or is this a separate thing?
No, this is a separate thing. This is where your network or hypernetwork spits out good parameters for the neural network that you would like to use.
So it's like reformulating your parameterization of it. Now your parameterization comes from like a
That's right, from this neural network. Okay. Yeah. Okay, so if you want to know more about hypernetworks, there's a review paper about it. So what I wanted to explore is what if you do quantum hypernetworks? So basically generalize this idea to a quantum state. Okay, and I'll show you why. So we introduce hypernetworks as a way to, or as a strategy to train binary neural networks. In a way, this is kind of like a natural idea. So, and we use them to unify parameter, hyperparameter, and architectural search for binary neural nets as a whole. So we can understand this training binary neural networks as if we're putting a bunch of neural networks or binary neural networks in quantum superposition, okay? And then this quantum state that we're going to produce with a quantum algorithm or a quantum state or a quantum device will spit the good choices of parameters and hyperparameters of the classical neural net. So it's the exact analogy with the hypernetwork, and that's why we called it a quantum hypernetwork, okay? So superpositions contain exponentially many binary neural networks with different parameters, architectural choices, and hyperparameters. The question is how to nudge the quantum state into producing good parameters and hyperparameters. And I don't know how to do it, but I'll give you what we did. So So what we do is we assign to each basis element in some sort of computational basis to a choice of neural network, okay? So basically, that's the reason why when we produce the state, we think of this as a bunch of neural networks in quantum superposition. And then, for instance, if you wanted to encode hyperparameters or architectural choices, what you do is you add one more qubit. Suppose you have two activation functions out of which you want to choose, then you can assign F1 and F2 and make this activation function qubit dependent. So you can add one more qubit, here's sigma 4, where this activation function depends on the value of the, I don't know, the spin projection or the qubit projection, either up or down. And so by doing this type of encoding, you can encode architectural choices, or you can encode hyperparameter search in your search. Yes?
What kind of activation functions are used for binary neural networks?
There's different choices, right? Like there's some probabilistic ones, there's some deterministic ones, and so on. We didn't explore those in here. We just, well, I'm going to show you some examples, but basically two, deterministic and probabilistic ones. Yeah.
So just out of curiosity, why would you expect having a quantum circuit feed into these effectively stochastic binary units that are feeding out of here? Why do you suspect that would be better than having a randomized algorithm feeding the exact same information in?
So it's basically a randomized way of producing this.
Yeah, exactly. So I'm just wondering, where do you expect the quantum secret sauce to give some advantage?
No, I don't know the answer to that question. If I knew, then I would be very happy, but I'm not. Okay. In fact, we're currently playing with replacing this with a powerful generative model, because that, in fact, produces kind of like the same type of algorithm that I'm going to be talking about.
It's probably pretty good at tensor networks.
And that's my last slide, okay? Using an MPS to, exactly. Okay, so let me continue with the story. At the end, I'll give you all those answers. And this is how you encode an architectural choice, but you can include other, other choices, skip connections, dimension of the hidden layers of the neural network, and you just basically add one or a few more qubits related to these choices, okay? So then we need to notch the state so that when we measure it in an experiment, it returns neural networks with good architectural choices, parameters, and hyperparameters. And this is the hard part. I don't have a good answer to that question, and I don't know the secret quantum sauce and so on. I don't have any of those answers because this is the first time I do this type of things, and this is where I do all the mistakes you both pointed out. I hope you forgive me anyways. So one idea is, of course, a variational quantum algorithm, okay, which, again, it's the only solution I know so far, but I'm thinking about some others. So a VQA employs a classical optimizer acting on a parameterized quantum circuit with the purpose of finding solutions to a problem encoding some objective function. And the objective function I'm going to be using is the objective function of the problem, of the machine learning problem, where we had this neural network output, the parameters, which are the weights and the hyperparameters of the neural network, and the data is xi and yi if you are having labels and you're doing supervised learning, for instance. And so basically what we do as a whole is we define an augmented model with parameters W, and these parameters encapsulate the neural network weights and biases, the hyperparameters, and architectural choices. Okay, so it's kind of like with respect to traditional machine learning definition of a model, we are adding everything, right? The hyperparameters and the architectural choices. And then, so this is a picture of this augmented model. So you feed the data. You have a neural network and the architectural choices, parameters, hyperparameters, and then out comes, the probability of an image given the label, or the probability of an image if you're doing unsupervised learning, okay? And this is what we're gonna optimize. And so So what we do is we do the simplest thing. We make this objective function quantum, quote unquote. We promote the parameters of the binary neural network or the model, and we promote them into a set of Pauli matrices. And so this objective function goes into an operator. In our case, I'm taking Pauli matrices, sigma z. So they become a big diagonal matrix where n is the number of variables that you're trying to optimize. Okay. Of course, this encoding is flexible, and in fact, this is very naive because we want trillions of variables here, as Nathan pointed out. And so this is going to be very inefficient, but let me explore it first. And then eventually we will have to go into better encoding of the problem. For instance, using off-diagonal operators, multi-basis encoding. You can take tensor products of Paulis and so on as your encoding and so on. For instance, they do in this paper where they encode in different bases, and they have perhaps a better scaling with respect to the number of variables in your problem. Okay, so that's the first thing, the first step. And then what we do is we do a parameterized quantum circuit, and we minimize the expectation value of this diagonal operator that we created, which is this thing here, and that we can estimate through sampling out of the quantum state. Yeah.
So I have a question regarding your design of parameterized quantum circuit. Is there any sort of information that you know from, say, take a classical architecture that has been trained and look at mutual information between some of your hyperparameters to know which qubits should be the more entangled? Is there any notion of producing good inductive biases here?
That's a great question, and as I said, I was making all the mistakes, and so we use Pauli gates and entanglements, as Maria suggested not to do. Okay, but of course I'm going to try and argue or reason through this a little bit, because the problem is we don't know a whole lot about this objective functions, right? Like, in fact, I looked at the machine learning literature about how do these look? Like, can we do something better than, say, taking inspiration from QAOA, which people have done, where like you have to, well, you use the knowledge of the Hamiltonian of the system plus some term introducing quantum fluctuations in some sense. So this is a perfectly reasonable solution. Taking inspiration from, say, quantum annealing, but it uses this here. It uses the fact that you would like to compile this object, which is hard to compile because we have not a whole lot of knowledge about what the structure of this objective function is, and so we don't know, or we didn't know at the beginning, and so we went for as I said. For the dumb Pauli gates and entanglers. All right. Okay, so I had a couple of slides about that. But now I went through them very quickly. So the design of the circuit is critical. The depth, the connectivity of the gates, the fact that you have to be able to implement them on a quantum device. And that we don't know a whole lot about how this objective function is a black box in general. And so how to choose a good answer was, well, you could use QAOA, but then it has the problem of having to implement e to the alpha, where alpha is some variational parameter, c, which is very difficult to compile. Yes?
Yeah, there has been a lot of work on this compiling the e to the exponential of c. That people call Hamiltonian simulation.
That's right.
If the c is sparse, you can do something. And if the c has some structures, you can diagonalize it, and you can do a lot of things. So that's a whole many years of literature behind that.
Yeah, exactly. So I agree with that. But the problem is C, in principle, contains all possible Pauli strings. So it
try to choose the ones you can implement.
Right. But we don't know which ones are important in principle. Okay, we don't know. So we know that, okay, there's going to be the identity, then the local fields or local Pauli Z, then using like two-body interactions, then three-body, four-body, all the way to N. And so there's a combinatorial explosion of possible combinations that you can input in the algorithm, and in principle, we don't know how to compute that expansion. It's, in principle, at least for Boolean, like for pure Boolean functions, computing this Ising expansion is as hard as solving the problem. It's Sharpie hard, if I understand correctly. So this is a real Boolean function. I don't know exact computational complexity statement, but it's at least naively exponentially hard to understand what the exact structure of the Hamiltonian of the C. So it's, as far as I know, it's hard to do. Mm-hmm.
But of course, that carries over to QA as well, right? I mean, one cannot expect a polytime algorithm for that task.
That's right.
But the C, of course, you need to understand the structure. So there is a whole field of continuous time quantum work behind that as well. So people do look at a wide range of structures of C, like topolers, like a lot. So I'm trying to say a lot has been done.
I'll ask you questions about this statement, okay? When I'm done. But thank you for the question. Okay. So yeah, so in the end we choose ansatz with polygates and entanglers. And then we do, so we have to run the optimization, and so we use gradient descent to optimize this using parameter shift rules. And so I'm obviously neglecting the barren plateau, as you suggested not to ignore, but that's what we do so far. So instead, in fact, we didn't even use samples to compute this. We do a full simulation, and we use tensor networks and automatic differentiation to do it as a first step. But then at the end, we use matrix product states with parameter shift rules, and we verify that we can still learn a little bit, at least on the order of 60 or 70 qubits. Okay, so it's not too bad. So let me show you some results. So this is MNIST. So it's a very, very tiny MNIST. It's, I think, 4 by 4. And neural network is just a perceptron, or a binary perceptron. And so what we have to do is we have to train the weights and biases. We run this optimization problem 200 times, and we compute or estimate the probability of finding an objective function, E theta, with some and we compute the probability that E theta is less than some sort of epsilon to define whether we're succeeding or not. So this optimization is successful frequently, and the optimal circuit depth is around here, 2 layers, so quite a short depth, is where we find the highest probability of finding a very low objective function. And so it means that, I guess, there's an optimal depth that you should be using, and then it starts to decrease, which is probably due to getting stuck on local minimum when you have very complicated, not very complicated, but a somewhat more complicated circuit in here. So in here you see these are the success probabilities of finding solutions with energy E theta, or value of the objective function E theta. And so what we find is that they're centered near the optimal value, which is around 0.32868. What's interesting too is that even a matrix, a product state, which Maria also mentioned, is quite successful. Okay, so basically you don't need any quantum effects to be able to successfully solve this problem. But a little bit of depth helps you, but the depth is not too deep. So this is an interesting result is for MNIST on a simplified value of simplified data set. So we wanted to do a little bit more. So we wanted, I don't know, this classification problem is very low dimensional, it's 2D. And the idea is to classify whether a point in this 2-dimensional space comes from the blue Gaussians or from the red one, okay? And we had this neural network, so it has this 2-dimensional inputs, a layer with 3 neurons and an output that tells you that's blue or that's red. And we had an activation function choice, and the choice was between a sigmoid and a ReLU, okay? And we wanted to find what the optimal parameters are and what the optimal activation function should be. And so we run the optimization 200 times, and we try and compute or estimate the probability of having an objective function less than some sort of epsilon, and we find the same, that there's an optimal sort of circuit depth at 3 layers that successfully captures or solves the problem with high probability. Same story, even a product state can do it. So a little bit of overshoot to go for, say, quantum circuits, but again, you gain something. You gain that you converge with higher probability if you use some sort of entanglement in the ansatz. Yeah.
You mentioned using sequence to switch activation functions.
Mm-hmm.
Do you have a way of implementing, like switching layers on and off? Is that what's happening?
You can do layers on and off too. And yes, so here is choice of architecture. So basically choosing between a sigmoid or a ReLU activation. But you can choose also adding layers or removing ones, all in superposition. Yeah.
Is that what's happening in these results?
No, in these results, what you're doing is you're selecting the choices of weights and biases and the choice of nonlinear activation. So the outcome of the algorithm is basically telling you should be using a ReLU. In this case, the best is a ReLU, and that's what the algorithm tells you at the end, right? Like it's telling you what are the optimal parameters and the optimal choices of nonlinearity. Yeah.
How does the size of the network play a role? Is that sort of an assumption also?
So the size of the network is very important. It's correlated with the number of qubits you use in this encoding of the problem. Mm-hmm. Yeah.
I have one more question. In this choice of the parameters W, right? There is no necessity to make that classical. You could make them quantum, right?
Yes, that's right, and that's one of the things, I think I mentioned it here. So this encoding is flexible, right? Like, so you could instead use, for instance, off-diagonal operators and different bases to represent different parameters and so on, and yeah. So there's no need to make them classical in that sense.
So in principle, you could have entanglement between the two pictures you have on your board there, right?
Yes.
You measure before you feed into the... but then you have quantum algorithms. You probably don't want that, right?
Quick case, if you had quantum states as your input rather than classical MNIST, you might just want to make the whole thing entangled and have no measurement.
Yeah, actually, and that's probably very realistic. You know, one extra qubit as an input state.
Right.
For many algorithms that I learned has many advantages. So a little bit of quantum overlap in W.
Yeah, that's right.
Maybe not a stupid idea.
Mm-hmm. Right. I never thought about it this way, but yeah.
Just a quick question, if you don't mind.
Yep.
Here, when you've got all of these measurements going in, could you view this as being kind of like the quantum hypernetwork as a particular implementation of boosting, where you've got now an ensemble of different classifiers that you have, where the weights are set by the probabilities of the outputs?
Yes, exactly.
Okay.
So in fact, everything I'm reporting is averaging over this distribution. Mm-hmm. Yes?
Yeah, quite a naive question. If you go to the other slides, you mentioned about nonlinear activation function,
mm-hmm.
right? And how do you do that nonlinear activation in the quantum sense?
So, yeah, that's a great question. So what we do, so when we're in principle using this for a quantum device, right? So what we do is we measure in the computational basis where we're solving the problem, and then we compute the objective function, the derivatives, through expectation value over this C objective function. And so at that point, you get the sample, and the samples are a bunch of different architectures and parameters for the neural net, but everything is evaluated classically. So then the nonlinearity really is just, in the quantum sense, is just up or down in one of the qubits. And then all the feed-forward process that you have to do, you have to compute it on a classical device. So all these nonlinearities will happen only on a classical computer. Does that make sense?
So it's post-selection. Are you talking about post-selection?
No, so basically, suppose you have one qubit that chooses which nonlinearity to use. Then you use that choice that you found out of the sampling of the quantum state, and then you use that information to perform the forward pass in the classical device.
Thanks.
Mm-hmm.
You could do it in a fully quantum world using fixed point amplitude amplification, but the cost of doing that will scale horribly with the depth of the network.
All right. I didn't know, but
thanks.
Thank you. All right. So, okay. So one more result before I'm almost done is so you can also, so here we do. So one architectural choice, which is nonlinearity, but then how deep, or sorry, how wide is your hidden layer? So we go from 2 to 3. So that's, again, so you have two choices, then you add one more qubit. If you have more choices, then you add 2, 3, and so on, okay? But in this case, it's just we're choosing only between 2 and 3, okay? And so we are choosing among those three choices, and then we do the optimization, we train weights and the two architectural choices, and then we find the same, right? Like that there's a product state can solve the problem, and that a little bit of entanglement or depth in the circuit boosts the probability that you find a good solution, okay? One thing is that the probability went down with respect to this. So here we were at a probability of 0.68 to find good architectural choices as the maximum, and here it went down, okay? So we're losing the power as we make the optimization more and more complex, which I think is expected, but that's something to be understood, or at least for me to be understood. Okay, so those are the results, or at least the initial results, but then we were wondering, any idea about the structure of C? So we can do a more careful study or a careful understanding of the structure of C on small on small neural networks. So that's what we did. So we did, we wrote what the effective Ising Hamiltonian looks like. That's called Fourier analysis in computer science. And it's basically, yes, so you compute the Ising Hamiltonian that would produce the exact same Boolean function that you had. And we do this by simply computing the Fourier coefficients, which are given by this trace over the objective function times the Pauli string that you want to investigate, and that gives us the exact expansion. So this is basically what's the Ising Hamiltonian that describes this thing. And then what we did is we summed over the square of this amplitudes or the coefficients in the Ising Hamiltonian as a proxy to identify how non-local this objective function is. And so basically for S Pauli strings or S Ising variables, we compute the amplitude square and sum, okay? And so these are the results. So this is for this exercise. So choosing nonlinear activation and weights and biases. And what we find is that it basically has a peak at 0, which is the identity. So it's just a constant, so it's not important. This is the single body, basically local fields. Then there's a peak at 2 bodies, so Ising pairwise interactions. And then 3, 4 body, 6 body, but then eventually it decreases exponentially quick. So that gives us some of confidence that maybe there's no issue with locality-induced barren plateaus, which was one of the issues that were raised, and related to your question related to how complicated is this function C. Maybe we can get away with 2 or 3 body interactions, and perhaps using e to the c, where you cut at some sort of order, is a good idea. Okay, so maybe, but the one thing I don't know is how to compute these coefficients for a generic neural net, so that we can go ahead and try and compile that unitary that's more principled as a choice for quantum circuit. Okay.
Can exponential decay be proven, or is just observed at the moment?
That's observed. So we don't have a proof. These are for the examples that we took, and just empirically computing what's the Fourier transform and analyzing the Fourier transform. But I don't think I have a proof that it always decays exponentially. It probably doesn't generically, but for some problems, I'm sure it should be very simple, because these problems are very structured. Okay, so this is for the second example. Sorry, for this example where we have architecture choices for the nonlinearity and the width of the hidden layer, and we see something similar. So a big peak at 1, some field, some local field, and then 2 body, 3 body, 4 body. Eventually, everything decays exponentially. Yeah.
So I've noticed a trend with all of your plots. It seems like almost always the last data point is an outlier. So I'm just kind of curious, like, say, for example, you look at the n equals 10, right? There's a nice pattern going up, and then, oh my God, the last point that you took a look at is different. Same as the n equals 18. Mm-hmm. So I'm curious, do you have more data than this, and just you didn't trust it, or?
No. So the thing is, it goes below machine precision. Sorry, no, this is for the entire number of qubits. No, I don't have more. I don't have more data. So this is where the expansion stops. So if you have 10 qubits, then you have at most 10 Pauli in the expansion, so you don't go beyond that.
I see. So then you kind of expect maybe a little bit of a difference once you hit the edge of that.
Yeah, so I don't have a good answer, because this is one valid term in the Ising expansion, right? Like when you have n or 10 sigma z in the function, and I don't know why it drops so much. Mm-hmm. But yeah, I never thought about it too carefully. But so this is again similar, and this is for the MNIST example, where you see again is basically the identity, and then you have local field mostly, and then it decays quickly. So this is the simplest, and perhaps the reason why even a matrix product state is even almost as successful as any deep circuits. Is just basically this is very close to a mean field solution, or a mean field should be able to capture this. Okay, so so basically that's what I just said. MNIST is nearly a single body Hamiltonian, which is easier to optimize even with a product state. I guess the only thing we did about barren plateaus seems like there's no tractability issues arising from vanishing gradients induced, at least induced by the cost function, because everything seems to be local and then exponential for like full, say, many body terms. It just seems to decay really fast. So hopefully there's no barren plateau issue, at least if you initialize smartly. Then there's a final comment about the augmented model. So we had this different way of training than people in machine learning use, right? Like, so we basically used an augmented model that encapsulates parameters, hyperparameters, and architectural choices for the neural net. And when we optimize only over all of them, as opposed to having this nested loop, where you optimize the parameters given architectural choices. So here we're optimizing everything simultaneously. And as far as I asked my colleagues at the Vector Institute, this has not been done in their experience. And so this asks or begs the question, like, can you do this? Can you really think about this enhanced or enlarged models. And what we did was we go and tested this hypothesis, right? Like, and what we did is, yeah, we computed the average function over the different as a function of training iteration for a different number of data points for this example here. So we choose like one architectural choice and the Gaussian data sets. And then as a function of training iteration, we see, of course, that the training and validation sets cost functions go down, okay? But when there's little data, for instance, when you have only 2 points in your data set, you see this, this behavior. So for the training, it goes down, but then for the test set, it goes down and then goes up, indicating that there's overfitting to the data. And what this suggests is that even though you have augmented the model and you have included all of these choices, that this behaves exactly as the traditional bias variance trade-off in machine learning, which is basically, I highlighted here, where you typically the error on the training set decays as you train the model, but then the validation error goes down and then goes up, where in this regime you're increasing the bias, and in going in the other direction you're increasing the variance of your prediction. So we were happy at least this choice or this argument for the augmented model behaves as you expect according to the bias variance trade-off, which is, if you want, one of the most important concepts in machine learning about like when it comes to choosing a model. Okay, so that's good news. So here it's only 2 data points, and that's the only point where we see the bias variance trade-off. The thing is, this problem is only 2-dimensional, so 2 data points already kind of like as big as you need for a problem to solve a problem, right? Like you never have enough data to cover not even the dimensionality of your space. So in here, beyond 2 points, you have too much data. So you see always decay in the validation set, okay? And the last slide is, again, doing MNIST, where we have slightly larger images here. We have 8 by 8. We have the 8 by 8 weights, 1 bias, and then we have 1 choice of activation function. But now we have, instead of 15 qubits, now we have 64. So it's a little bit of a better size, a little bit of a bigger problem in some sense. And then we run MPS, matrix product state simulations, with a depth 2 for the quantum circuit. And then what we see again is similar. We successfully find the solution to the problem. This is still very small for a size of a problem in machine learning, but nevertheless, it gives us some confidence that we can at least try and handle slightly bigger problems. Okay, so let me conclude. So we introduced the idea of a hypernetwork or a quantum version, in which we train binary neural networks in quantum superposition, quote unquote. We have only one optimization loop that trains parameter, hyperparameters, and architectural choices in this binary neural nets. So this is very different from what people in machine learning do traditionally. So if anything, this is perhaps the most interesting result, at least regarding what we do different with respect to machine learning. And it's completely unexplored, even apparently in the classical ML literature, as far as my friends could tell me, the ML experts at the Vector Institute. So we had this horrible encoding. We only choose the Z basis, but we could do what you suggested, or choose different Pauli strings as a way to encode more, or pack more weights and more information in the quantum circuit. So the speculation that we had is that binary neural nets save energy at inference time, and we're suggesting that we can potentially save energy training everything together. Okay, so architectural search, hyperparameter search in one. So this is not a quantum thing. This can be done classically and on a quantum device. But people speculate that this is a quote from a paper, I forget to cite it, but quantum computers are currently reaching the ability to vastly outperform supercomputers' energy efficiency. So we're thinking, can we use this, or can we speculate that this can help alleviate this energy efficiency issues with large language models eventually if we keep doing this or keep exploring these ideas. Anyway, that's it. Thank you so much for the attention and the questions.